Ladies and gentlemen, welcome to this plenary session. It's my honor and my pleasure both to present to you Grazia Speranza, currently serving president of the International Federations of Operations Research Society, and she served our community and full professor of operations research, denominated professor of operations research at the University of Brescia. Whenever I chair a plenary, I try to be brief, at least shorter than the abstract, but this time I cannot do it, basically. Sorry for that. Grazia served the OR community in many different, very important, very key positions and activities. It's impossible to cover all of her research achievements. Yesterday I looked up the number of citations in Google Scholar. It's above 8,400, which is something, which tells us something. I think it's more than 200 articles in refereed high-level international journals, plus conference proceedings, very important outlets. She already left her print on our field, in particular in the field she will present some aspects today on transportation supply chain management. And given that time has proceeded, I won't take more of your time. Grazia, the floor is yours.
Thank you very much, Emmanuel, for this very nice, very kind introduction. And thank you to the organizers for inviting me here. It's really a pleasure. It's a beautiful conference, fantastic location, but you have done an amazing job, and everyone is so happy to be here. So thank you very much. So, yes, operations research in transportation and supply chain management. I started working in transportation at the very beginning of my career. And over the years, in fact, I have tackled different problems, and not only in this area. And I have learned also many things from my experience in other areas. And I think what I have learned is to try to move on, always, to try to understand what are the challenges in front of us. And I'm trying to do the same also now. Nicholas Hall, in his lecture, the first day told us about the challenges that our community is facing these days because of the technological evolution. And we hear around us a number of, words, buzzwords, expressions. Sometimes we understand what they mean, sometimes maybe we don't do. We try to understand precisely, but sometimes these words are a bit vague, but they indicate that things are changing. The Internet of Things, the IoT, we have sensors and devices everywhere collecting information, data, and delivering, transmitting information. Big data, data everywhere, provided, offered by all these devices. Artificial intelligence has been around for many years. I remember at the beginning of my career, my colleagues in computer science, they were talking about artificial intelligence and language recognition and vision and everything. Things have been around for a long time, but they're becoming real now because of new techniques, especially machine learning and deep learning. And the sharing economy, this also around us, the sharing of underused goods of all sorts, cars, planes, food, everything. Now it can be shared because we have the opportunity to communicate among us through our mobile devices or in all the different ways that are made possible by the technology. In particular, in transportation logistics, things are changing very rapidly. And transportation has become a very hot area, not only in research, but also in practice. Traditionally, in our area, our community has been divided in two big streams. One working on freight, transportation, supply chain management, logistics, where the things that move are items, objects, parcels, whatever. And another area, stream of research on people transportation. And most of our contributions there have been on how to schedule cruise, how to schedule trips in the air business, the air flight business, in buses, in trains, and so on. But now I think these two areas are not as divided as they used to be. There are merging points, and also the two streams, freight and people, in some situations merge. Our community has given in supply chain management, logistics, it used to be logistics, it has become supply chain management in the last, 20 years because of the information systems that allow companies to communicate. So now we don't only tackle a single company, but we tackle we can tackle the entire supply chain, the suppliers and the customers of companies, and in principle, the entire supply chain. So everybody talks now about supply chain management rather than logistics. Our community has given many contributions, many different areas, from design to inventory management, scheduling, location. We know these areas very well. Our own books, we have thousands of papers. And these contributions are so mature that they have become part of software. We find packages sold to companies that embed our models, our contributions to the improvement of the efficiency of companies. What is happening? Where are we going? What are directions where the research is going in supply chain management? I believe there are these four major, I would say, trends, words, I don't know how to call them, but I perceive that these are the words that people feel are driving the research in this area. And systemic is one, so we can move towards more integrated models. Collaborative, because companies can collaborate, people can collaborate, individuals, companies, institutions. Dynamic, because we have data coming continuously, and then we have to move towards more dynamic models and more dynamic approaches to optimization. And data-driven, because we have plenty of data and we have to take advantage of the data that become available over time. I will try, I cannot cover all these sort of trends and forthcoming research, but I will try to give you a few examples, of course, through my own research in the last years. So about systemic direction. So we are moving towards integrated problems. In this supply chain management here, but also in all the companies in this area, the conferences in this area on supply chain management or transportation, you can see more and more papers that combine scheduling with inventory management, production and inventory, transportation and facility location, combination, integrating. So I will give you an example now of this kind of approach, but there are many others. So take production routing problem. Production routing problem is a problem where you have a factory, or you may have several factories. You have distribution, you have inventory, and you want to reach the final customers. And you have different costs, fixed production costs, inventory costs, and we know this very well. We can handle lot sizing problems very well, right? And we know also distribution very well. We know how to do the routing very well, and then we have inventory costs. But what changes here is that we want to tackle the whole problem altogether. Is there an advantage in doing that? So I would like to show you that there is a big advantage in integrating. So this is the objective function. There are several variables. What I want to show you, how to compare and what is the advantage of tackling this problem through an integrated approach with respect to sequential approaches. Of course, the whole problem has been around in all companies, right? All companies have to produce and distribute. And usually what we assume is that there is a sequence of decisions. So you may first produce and decide how to produce, and then you distribute, or vice versa. You may distribute first and then to produce, right? These are sequential approaches. And through the models, the traditional models that we have, lot sizing and routing and inventory management, we can use these kind of approaches, and we know how to do that. So if we want to compare the sequential approaches and the integrated approach, we have to solve them all. So now I'm showing you very briefly how to build solution approaches that allow us to compare the sequential and integrated way of solving this problem. So production first, distribution next. If we produce first, then we have to decide what to produce, minimizing the cost, without knowing what our customers need, how we will distribute day by day. So the challenge here is to estimate the quantity to be distributed at time t, without knowing how you will distribute in the optimal way, because you produce first and you distribute next. I will not give you the details, but at the end, assuming some way of distributing the goods, we end up in solving a lot sizing problem, and this will give us a production plan. Given the production plan, then we distribute, and the problem here is an inventory routing problem, right? If we distribute first and produce next, we have a similar challenge, because if you distribute first without knowing how the production is made, we have to assume somehow how the production will work, and then we have to estimate the quantity produced. We have experimented ways of doing that. In any case, we have to solve also here an inventory routing problem. So after the distribution, we have the production, and here we have to solve a lot sizing problem. So we need these algorithms. We have this problem, the lot sizing that we solve with Cplex. We have the inventory routing problem, and we picked up code developed in previous works. And we have the production routing problem, and we have used a variant of a heuristic presented in a previous work. So we have these ingredients, and now we can compare the sequential approaches and the integrated approach. And these are the results. These are the numbers for going from top to bottom. The setup cost increases, so the production cost becomes more relevant with respect to the transportation cost. And then you see the cost the cost reduction. If you integrate with respect to the sequential approach, the cost reduction reaches, in this case, 17%, 47%, big numbers. If you think of the lot of effort that we put in improving a heuristic with an error that drops from 5% to 3%, here we have big improvements in a different way, just tackling a different problem, looking at a more integrated system. And if we go to bigger problems where we don't have the exact solutions, we have similar numbers. These are the average. Cost reduction due to the integration, and these are the maximum values. So depending on the instance, of course, you may have big or small, I would say huge or medium cost reduction, but you always save a lot. So this one direction. Collaborative direction. There are papers on how to collaborate. There are different ways. In a supply chain, you may have companies at the same level collaborating at different levels, hierarchically organized in a supply chain. So there are different ways to collaborate. Also, you may have collaboration between competitors, and they collaborate, they share warehouses or other resources. You may have collaboration within the same supply chain, and also you may share the capacity of vehicles, or you may share orders, because my orders will be served by you, because it is more convenient for you to serve my orders because I'm very far from my customers, you are very close, for example. So, collaboration between companies. An example. In this example, we have companies that have their own depot, they have their own customers, and in fact, what happens often in practice is that companies that have to serve customers that are very inconvenient for them because they're far away, or they request an amount of goods that exceeds the capacity of the trucks by a little, and then it is not convenient to send a full truck, they use their competitors to serve their customers. This is done on an individual basis. I phone you because I know my competitor, and I ask you to deliver something that I should deliver, and this is how things are done. So, in general, we have modeled this problem by saying each company decides which are the customers that each company decides which are the customers it wants to serve, and which are the customers that are not conveniently located, that do not have a convenient quantity requested, and then these customers are shared with the others. So there are customers that each company will serve, and customers that are sort of put in a basket and will be organized in a common way between the different companies. So, in this example, we are talking about a horizontal collaboration because the companies are at the same level. They may and are in general competitors, and they share orders. So, an example, we have, for example, a red company which has to serve these customers, and the blue company that has to serve these customers. And as you can see, there are customers that are in the same areas. Maybe not exactly the same, but they are in the same areas, this and this. So it may be convenient for the two companies to sort of talk to each other, and one company may serve a customer of the other, and vice versa, depending on the situation. But in any case, there may be a need to transfer goods between the depots of the two companies, but it is worth studying what happens and what are the advantages of this kind of collaboration. We can do, and we did some kind of analysis, you can show that the cost may be reduced by a factor, which is the number of the companies. So you may have big advantages. Of course, it depends on the location, the capacity of the vehicles, and on the quantities requested by the customers. And so this is a worst case analysis. And if it is guaranteed that in the collaboration, the profit of each company does not decrease with respect to any sub-coalition, the solution of the optimization problem belongs to the core of the game. So in the case of two companies, it is sufficient to impose that the profit in the collaboration is, for each company, is greater than the profit of the company in a non-collaborative environment, then the solution of the optimization problem belongs to the core of the game. So formulations, we try different formulations. So we can use, I'm showing these just to tell you that we use the same tools that we use, our OR tools, just to show different ways, different things. So we tested different formulations. We developed solution methods, cuts for the two formulations. And then we tested different sets of instances, different size of instances. And in this square, the red company has its own customers, the blue company its own customers, the green customers are shared. And then we have to decide how the routes of each company are organized, who will serve the green customers, assuming that they share the revenues coming from these shared customers. And of course, we need a collaboration scheme, a revenue sharing scheme that we have to put into the model. So we compare the two formulations. In this case, the load-based formulation works better. And then we have the savings. Here are the savings, and again, you see the numbers are not 0 point or 1 point or 2 points. There are big savings that can be achieved. And you can show also that the number of vehicles used is reduced through the collaboration. So there is a lower environmental impact, less pollution, a number of advantages, not only economical, but also environmental impact. And similarly, with different instances of different size, you have these kind of savings differently distributed between the companies. And one of the issues that we're studying now is how to distribute the savings among the companies, because you may have an unfair distribution of the savings, and of course, although each of the companies will save, the savings may not be distributed in a fair way. So this is a key point that we will tackle in the next Freight and people. I told you at the beginning that our community has tackled the two streams, the two kinds of problems separately, and often in conferences, people do not even talk to each other. So people in freight transportation go to the freight stream sessions, and in people transportation, they go to their sessions. And I think now the things are changing. Crowd driving, occasional drivers. The square represents a supermarket, for example. And a regular customer goes to the supermarket, right? Does the shopping, goes home, back home. And then, more and more, there are online customers that stay at home, make an order through the internet, and expect the shopping to be taken to their home. They don't move. They don't want to move for many reasons, right? So, it is a big cost for the companies to serve these online customers, and there is a big competition. And companies are trying to, the supermarkets are trying to charge the customers a short amount of money, a small amount of money, but at the same time, it is a cost to send out a driver, the time of the driver, the vehicle, everything. It's an expensive service. So the idea that some big companies working in this business, such as Amazon and other big companies, big players in this field, have started experimenting this kind of solution. So suppose that you ask your regular customers if they are available to become occasional drivers, if they are available to deliver on their way home the shopping bags of someone else. So, for example, I'm a regular customer. On the way home, I serve also a customer which is not too inconveniently located with respect to my destination, to my home, right? And then, of course, the supermarket has to serve the other online customers with a regular vehicle, a regular driver. But if the number of online customers it has to serve with its own vehicles decreases substantially, the cost of the service decreases and so on. Of course, the supermarket has to compensate these occasional drivers somehow. The problem now becomes to minimize the sum of the cost of serving the customers with regular drivers and the compensation that we have to give to the occasional drivers. So, this is the problem. And there are challenges that have to be faced. For example, somehow we have to model the behavior of the occasional drivers because they will not be always available to do that. What is the right compensation schemes, and the objective is to minimize the total cost for the distribution. How do we model in this paper that I mentioned? How do we model the behavior of the occasional drivers? Through the detour that the regular customer, the occasional driver, is available to do. So if the detour is small, we assume that the occasional driver is available to perform the delivery. And if the detour is too big, he or she will not be available to perform this service. This is the way we have modeled the behavior of the occasional drivers in this paper. And then we experimented different compensation schemes. It may seem trivial, it is not at all. So you may pay the occasional driver on the basis of the distance of the customer that has to be served, because you want to avoid serving faraway customers. You are very happy as a supermarket if you do not have to serve a faraway customer, so you compensate more for customers that are far from the depot, from the supermarket. And another way is to pay proportionally to the detour. In the first case, we don't have to ask our occasional drivers what is their home address. In the second case, we have to ask them what is their home address. So there are also privacy issues depending on the schemes that we adopt. We have our regular optimization model where there is a parameter that is the compensation to the drivers, to the occasional drivers for the service of a certain customer, and this depends on the scheme that we adopt. All the variables are binary. We solve the model exactly up to the size we can, and then we develop the math heuristic, and then we perform some experiments to see what happens. And in this figure, you see in blue, the online customers that we have to serve. Our supermarket has to serve these online customers, and in green, we have the occasional drivers, right? So now this is the solution if we don't use the occasional drivers. So the green are the regular customers that have declared to be available to do the service in principle. So if we use a compensation scheme proportional to the distance, this is the solution. If we use a different scheme proportional to the detour, we have this kind of solution with one vehicle only that we use. And if we have the same scheme proportional to the detour, but where we give to the occasional drivers a lower compensation, then it becomes convenient to allow the red area here to be served completely by the occasional drivers. The point is, are our occasional drivers available to accept a lower compensation? So the modeling of the behavior of the occasional drivers is key to this research. And I think in the future we will see more research trying to answer or partly answer these questions. These are the savings. So again, of course, we can achieve big, medium, small savings depending on the situation, depending on the instance, depending on how good the service is organized, how easy it is for a regular customer to become an occasional driver. There are so much uncertainty around what will happen in the future, but it is something that certainly will be studied in the future again, certainly by companies. I mentioned that one of the key points is the behavior of the occasional drivers, and I just wanted to mention a research that we have done recently, a sort of continuation of the previous research that I have just presented. And suppose we have in the red circles, we have a normal person who has to go for some reason from Acireale to Palermo, right? And then suppose that we have a parcel that has to be shipped from Catania to Cefalù, maybe containing some fantastic cannoli, for example. And then the point is, again, to organize things. We have many of these situations, of course, not only one. We have many people traveling around Sicily. We have many parcels that have to be delivered around Sicily, and we have to organize the possible assignments, the possible assignment of parcels to customers so that things are delivered by people who are traveling in any case. So again, cost reduction, environmental impact, and all positive things, because the cars that are on the road, because a person has to go from Acireale to Palermo, will go for two reasons, because the person has to travel and also with the parcel. So parcel and people, goods, freight, and people travel together. And this is what the work we have done recently, and it's a recently submitted paper. Finally, transportation of people. Well, things are changing. We know very well. Electric cars, electric vehicles. I remember again, we have heard of electric vehicles for many decades, and now it's happening. It's happening. So it's a matter of time, but they're coming. The cost is decreasing, and more and more hybrid models, but also fully electric vehicles are becoming available, and we are starting to think about buying one, right? Connected vehicles. Things are changing here too. The vehicles are connected through the internet, the data are coming, we have traffic information. We can deliver also, we can send out, transmit messages or information from our vehicles. In principle, these will become more and more, will be developed in the future very much, certainly. And autonomous vehicles. In the US, there is a huge investment on autonomous vehicles. All the research, well, not all the research, but a lot of research is being made by our colleagues on autonomous vehicles. There is still a lot of debate around how to implement these vehicles, how to make them safe. So a lot of challenges, but again, people believe it will happen. It is a matter of time. Directions in people transportation. Car and ride sharing. If you think about how much of your car is used with respect to the time it is kept in the garage, it's nothing, it's epsilon, right? Because the car has 4 or 5 seats, can be used 24 hours every day, and we use it how much? 1 person, 1 hour, so small percentage. So someone believes that the cars will disappear, we will not own the car in the future unless we will be enjoying driving. We want to do something exciting, but not because we have to go to a place, because we have to work. On-demand services. Again, if you think about things are changing. In the past, we had buses, trains, mass transit systems, and taxis, or our vehicles. In the middle, nothing. Uber is coming, ride sharing, car sharing. Still, these systems are often a cost to the municipalities because the mass is not there. They are not economically beneficial because of the size of these systems. And I think here something will happen in the future. And route guidance. Kind of ride sharing practice. What we are observing also, I think, is that somehow industries, companies, businesses are ahead of research. We are following things that have already happened. We are not driving the ideas. The business is driving us. So we see things around, and there are interesting problems to study here, right? So let's take again Acireale and Catania. Well, our GPS systems in our cars have been around for a long time, right? And we know inside there are shortest path algorithms, because when we ask the GPS to give us the path to our destination, it finds a path. The path. We can choose the shortest in length, the shortest in time, but this is the thing. I tried for the route from Acireale to Catania, and Google Maps has given this only path, right? And there is a reason, because there is no congestion here. So one path is simple. You're not given options. But if you try different parts of Italy, for example, the path from Brescia to Milano, and you want to go from Brescia to Milano, Google Maps gives you 3 paths. It gives you this in blue, which is supposed to be the best, but it gives you 2 other paths, right? You see here, 2 other paths. Why? If there is a best path, why 3? The point is that it is not clear what is the best because of congestion. So along the path, things are changing. So, and often, I don't know if it happens to you, although some systems offer you the shortest path, you may not believe this is really the best, and you choose another one because of traffic conditions. Information on traffic are embedded now in some of these software, like Waze. So things are changing here too, and there are new problems to study, but this is something that is worth studying. So if we go to the literature on traffic assignment, we see that there are these well-known and well-studied traffic distribution systems. The user equilibrium, and the system optimum. In the user equilibrium, each driver behaves in a selfish way. So I just do the best for me, right? And in an equilibrium of the network, in an equilibrium situation of the network, each user will experiment the same traveling time. And the system is in a Nash equilibrium. There is no advantage for anyone to move from a path to the other. Each is doing the best for his or her own. But the point is that we may end up with congestion, right? Because Emmanuel wants to go from Brescia to Milano, and it follows the shortest path. I want to go from Brescia to Milano. I follow the same shortest path. And also Patrizia is going to Brescia, from Brescia to Milano. No one is coordinating our decisions. In the system optimum kind of solution of traffic distribution, we have a minimum total travel time. So there is a less traveling time. So we would travel less, and we will not experiment congestion. The point is that the problem is that some drivers would experiment very long traveling times. So Emmanuel would be sent a long path, I would be sent to the shortest path, and probably Emmanuel, after a while, would move or would not follow the direction. So the system optimum solution has never been implemented. It is a theoretical kind of study, and the price of anarchy is the difference between these two kind of solutions. In 2005, Rolf Möhring and his co-authors have published in OR a paper, which is the first paper where they found, through the solution of an optimization problem, a traffic distribution, a traffic assignment that limits the length of the path. So Emmanuel may have to go to Milano through a slightly longer path than me, but not by more than a given percentage. So we limit the difference, the unfairness between drivers that have to go from the same origin to the same destination. And this makes the solution, of course, more likely to be accepted. And if you think about autonomous vehicles, this is becoming an option that may really become interesting. So we have some recent works in this direction when we are continuing to work in this direction. The expression here is the expression that people working in traffic know very well. It is the time needed to traverse an arc, given that this is the capacity of the arc, and this is the number of cars on the arc, and this is the time without traffic, the free flow traveling, the traveling time in free flow condition, which means without traffic. So basically, since we have to decide the x, so how many cars travel along an arc, we have a nonlinear problem. So this is a nonlinear optimization problem, and the number of paths is exponential. So there are computational challenges here to face. And in this recent work, we have presented a model where we minimize a piecewise approximation of the nonlinear function that models the total travel time, and we have then imposed constraints, and without going into the details, we have an exponential number of binary variables. We have implemented a heuristic, which is a heuristic column generation to make the problem computationally affordable. And so the heuristic generates new paths, solves a restricted subproblem, and loops until we find the reasonable solution. We have instances that we have tested with this structure, also some real case instances. There are benchmark instances that you find on the web, and this is the kind of solution that we obtain. So here we have the percentage of increase of the traveling time by manual with respect to me. I'm assuming I'm traveling along the best path. Manual is likely, will experience slightly, but not much. So 1% more, 2% more, 3% more, right? So very small. I tell you that often I would be very happy to have a guarantee that I will travel 2% more than the shortest path, right? So, this is the curve of the system optimum solution. This is the total travel time. So the minimum possible travel time, total travel time, is achieved by the system optimum with possibly very long paths and very, very much unfair solutions. Users will not be happy, right? Then here we have the user equilibrium solution. And here we have the solutions of the two models that we have implemented that converge quite rapidly to the total travel time of the system optimum solution, depending on the level of difference between the paths from origin to destination. So it seems a promising kind of approach. Right. So the future, what will happen? Who knows? Drones will be in our skies, delivering parcels, maybe. We may have lanes for autonomous vehicles and normal vehicles. Who knows? Maybe, probably. I have met recently Giampaolo Dallara. Some of you may know his name. He is a producer of sport cars. And of course, people listening to his talk ask him, are you afraid of what will happen in the future? The number of cars produced will decrease, probably because if we share vehicles, the number of cars produced will decrease. He said, yes, we are very aware that things are changing. We are prepared to the change, but we believe that people will keep enjoying to drive. They will not drive because they have to. They will drive because they enjoy it. So to go out on Sunday with the family, whatever, to go to the mountains, they would use their own car, but not to go to work. So thank you very much.